In number 17, we're trying to draw a rectangle inscribed inside an ellipse, and we're trying to make that rectangle as large as we possibly can. Now, I wouldn't be shocked if some of you guys looked at this problem and said, no way, I didn't really learn much about ellipses in the past, so I'll walk you through some of that, but honestly, you really don't need that much information about an ellipse. In this optimization problem, just like every other optimization problem, step number 1 is to set up your parameter, the relationship between x and y that has to hold true, and anytime there's an equation given to you, such as this one right here, that equation is your parameter. That has to be the relationship here between x and y at any point that we choose. Now, that said, let's talk about how to graph an ellipse in case you forgot this or in case you never learned it. In an ellipse, actually same thing with a hyperbola as well, we don't like it equal to 9. We really want it to be equal to 1, and that means that we're going to divide each term in this equation here by 9. So that means we're going to end up with something like x squared over 9, okay, plus a 4y squared over 9, all of which is going to equal 1. So what does that look like in terms of a graph? Let me draw this in black here real quick. Okay, so an ellipse, hopefully you'll remember, is kind of it's an oval, essentially. There's no h's and k's here because there's no number being added or subtracted from the x or the y. What's going on right here is that this number underneath the x squared, 9, if you take the square root of that number, which is 3, that tells you how far you're supposed to go to the left and the right here to figure out the length of this horizontal axis. So what that would tell us here, guys, this is not important, you don't need to write this down right here, but that a is equal to 3, and that means we're going 3 units to the left and 3 units to the right, and the ellipse passes through those 2 points. Now, we would do the same thing with y to figure out what b is right there, but the b is complicated a little bit by the presence of the 4 up on top. But essentially then, what's going on with that term right there is that b is the square root of 4/9, which ends up being, let me think about that for just a second, is that 2/3 or is that a 3/2? I think that's a 3/2 we end up with right there. And that would tell you that this graph is going to go 1.5 units up and down along the y-axis here, there and there and there and there. So now I'm pretty sure I've got 2 points that are located here and here that the ellipse is going to pass through as well. Now, if you weren't 100% sure, you could always double check this. Like, for example, I'm pretty sure that my ellipse passes through the point 3, 0. Let me try plugging that into this equation right here. Does it work? 3 squared is 9. 0 squared is 0. 9 equals 9. Yeah, that one works. And this one right here, this is the one I'm curious about, I got 0 and then 3/2. Does that work here? That would be a 0 plus a 4 times 3/2 squared, which is 9/4, should equal 9. Well, yeah, sure enough, those 4's cancel, and we get 9 equals 9. So, okay, I got that one right, even though I haven't done this in a long time. So that means that my ellipse is an oval centered at the origin that passes through those 4 points. Maybe didn't draw that perfectly, but close enough. And now what we're going to try to do is locate a rectangle inside or inscribed in that ellipse right there that's going to have the maximum possible area that we want. Now, if instead of an ellipse, this was a circle, it'd be a pretty easy problem. We'd be drawing a square inside that circle in red. But since it's an ellipse, things are a little bit different. Now, once more, this is a floating dot problem. And what I'm really interested in is that ordered pair right there, which is x, y. And that's going to help me figure out the area of that rectangle. So let me leave some space under step 1, and here we go for step 2. We're trying to maximize the area of the rectangle here. So we need a formula for area, and we've seen something like this before. The point xy, that's the distance that you would travel from the origin to this point right over here, x to the right and y units up. That means that the whole rectangle is going to have a base of 2x, and it's going to have a height here of 2y. So area of the rectangle is 2x times 2y, which is going to be a 4xy. And at this point, I have to go back to step 1 and make a decision now as to whether we want to solve for x or for y. Well, because the y squared has a 4 in front of it, I think it would be a lot easier if we solved for x instead. So I'm going to go with that. X squared is equal to a 9 minus 4y squared, and then we'll take the square root of both sides. Oh, that should have all moved at once. All right, we're going to take the square root of both sides of that equation and get x equals the square root of 9 minus 4y squared. And I'm going to make that substitution right in there for that x. So area as a function of y is going to be 4. Let me go out of order here. Now that y is going to come here next, and the x gets replaced by this square root of 9 minus 4y squared. And because of the square root there, even if I took the time to rewrite this as 4y times 9 minus 4y squared to the 1/2 power, distributing the 4y isn't an option because of that 1/2 power there. So I'm going to have to leave a of y right there and move on to step 3 where things might get a little bit ugly. A prime of y is going to be the derivative of this expression here, which is going to require the product rule. First factor, 4y, times the derivative of the second. That's a 1/2. Same base now, 9 minus 4y squared to the negative 1/2 times the derivative within, which is a negative 8y. So that's first times derivative of the second, plus the second factor, 9 minus 4y squared to the 1/2 times the derivative of the first, which is just going to be 4. And we want to set that derivative equal to 0 and solve that. And this looks like it's going to take some work, everybody. So let's see what we can do. I'm going to clean up that first, that first term right there. The 1/2 and the